The night was calm. No storm. No enemy fire. No collision. At the dock in Portland, Oregon, January 16, 1943, the SS Schenectady sat still in the water, freshly built, fully loaded, engines silent. Sea trials were over. The ship had done everything right. Then, without warning, a sound tore through the harbor, a crack like cannon fire, sharp enough to send workers running from the pier. The deck of the Schenectady split open in a jagged line, stem to stern. The hull groaned, buckled, and broke nearly in half. A ship built from 100,000 tons of American steel had torn itself apart while doing nothing at all. No torpedo struck it. No wave battered it. It simply cracked. This was not an isolated failure. It was the visible edge of a problem hidden inside thousands of ships, a flaw built into the very method that had made American shipbuilding the fastest in the world. The United States was producing cargo ships faster than any nation in history. A new one launched every day, sometimes several. Speed had won the war of production. But speed had also introduced something no naval architect had fully understood, a way of building steel hulls that could shatter like glass in cold water. The Liberty ship program would deliver over 2,700 vessels, and a number of them would break. The story begins in 1941, more than a year before the Schenectady's hull gave way on a quiet dock in Oregon. Britain was losing ships faster than it could build them. German U-boats prowled the North Atlantic, sinking merchant vessels carrying food, fuel, and war material to a nation fighting for survival. The math was brutal and simple. For every ton of shipping sunk, a ton had to be replaced, and replaced quickly, or the war would be lost before American troops ever crossed the ocean. The United States needed cargo ships. Not dozens. Not hundreds. Thousands. The design chosen for the job was not elegant, it was not fast, and it was not built for comfort. It was a simple boxy vessel roughly 440 feet long, powered by an old-fashioned steam engine, capable of carrying more than 10,000 tons of cargo at a modest 11 knots. Naval architects and shipbuilders privately called it homely. Some called it worse. President Franklin Roosevelt himself reportedly referred to it as a real ugly duckling. But ugly did not matter. What mattered was how fast it could be built. That question fell to men like Henry Kaiser, an industrialist who had never built a ship before the war, but had built dams, bridges, and highways, using the principles of American mass production. Kaiser looked at shipbuilding the way Henry Ford had looked at automobiles a generation earlier. Break the process into standardized, repeatable steps, and the speed would follow. Steel sections were prefabricated away from the shipyard, in some cases hundreds of miles away, then transported to the ways and welded together into a hull. Workers who had never built a ship in their lives, many of them women, many of them new to industrial labor entirely, were trained to perform single, repeatable tasks with speed and precision. The results were staggering. What had once taken the American shipbuilding industry an average of about a year to construct now took weeks, then days. In November 1942, at Kaiser's shipyard in Richmond, California, the SS Robert E. Peary was laid down, built, and launched in 4 days, 15 hours and 29 minutes. A stunt timed deliberately for a war bond drive, but a real hull nonetheless, built from keel to launch faster than any ship in the history of naval construction. The record stood as proof of what American industry could do when survival demanded it. By the time the war ended, American shipyards would deliver over 2,700 Liberty ships, more tonnage than any single class of vessel ever built, before or since. It was by every measure available at the time one of the greatest industrial achievements in the history of warfare. What no one fully understood yet was the price of that speed. It was hidden not in the design, not in the men who built it, but in the welds holding the steel together. Welds that made construction faster than ever, and that carried inside them a flaw the shipbuilding world had never encountered at this scale. For as long as steel ships had been built, they had been held together the same way: rivets, red-hot metal pins driven through overlapping steel plates, hammered until they cooled, and fused the plates into a single, If imperfect, whole, it was slow, brutally labor-intensive work. A single Liberty ship hull required roughly 3 million rivets, each one placed by hand. Each one demanding a skilled crew of at least 4 workers, a heater, a catcher, a bucker, and a riveter, working in dangerous, deafening conditions. Riveting was also, without anyone fully realizing it at the time, forgiving. A steel plate is not one continuous sheet in a riveted hull. It is thousands of individual pieces, joined at their edges by rows of overlapping seams. If a crack began in one plate, it had nowhere to go. The seam itself, the joint, the overlap, the row of rivets, acted as a natural barrier, absorbing the stress and stopping the fracture before it could spread. Shipbuilders did not think of this as a safety feature. They simply built ships the way ships had always been built, and the ships, for the most part, held. Welding offered something riveting never could: speed. Instead of drilling, aligning, and hand-riveting 3 million individual pins, a welded hull could be assembled by fusing steel plates directly to one another, edge to edge, into a single continuous surface. No overlapping seams, no rows of rivets eating into the shipyard's schedule. A welded hull could be built in a fraction of the time, using a fraction of the skilled labor, at a fraction of the cost. For a nation racing to outbuild German U-boats, the choice was obvious. By 1941, American shipyards had shifted almost entirely to all-welded construction for the Liberty ship program. The engineering logic seemed sound, even superior. A continuous welded seam distributed stress evenly across the hull, naval architects reasoned, rather than concentrating it at thousands of individual rivet points. On paper, and under the loading conditions engineers knew how to calculate, a welded hull was not just faster to build, it was structurally stronger than anything riveted. What no one had tested, because no one had ever needed to at this scale, was what happened when that same continuous steel encountered cold water, sudden stress, and a hull design with sharp structural angles at the corners of hatches and deck openings, points where stress naturally concentrated far more than engineers of the era appreciated. In a riveted ship, a crack starting at one of those points would run into a seam and stop. In a welded ship, there were no seams. There was only steel, continuous from bow to stern, offering a crack and nothing to stop it once it began. The very quality that made welded construction faster and, in theory, stronger, had also removed something the shipbuilding world had relied on for over a century, without ever fully understanding why it mattered. Nobody had designed that protection on purpose. Nobody had known it was gone. The first ships would sail for months before anyone found out what that absence would cost. The first sign of trouble arrived quietly, buried in shipyard inspection logs and captains' reports that few people outside the maintenance crews ever read. Beginning in late 1942, reports started coming in from Liberty ships operating in the North Atlantic and the cold waters off Alaska. Hairline cracks appearing in deck plating, sometimes just a few inches long, sometimes running several feet before stopping on their own. In most cases, the ships kept sailing. Repair crews welded patches over the cracks, logged the incident, and moved on. War production did not pause for a few inches of steel. The explanations offered at the time were mundane, even reassuring. Some blamed poor welding technique, an understandable suspicion, given that so many of the welders working in America's shipyards were new to the trade, trained in a matter of weeks rather than years. Others pointed to rough handling during loading, or simple wear from heavy seas. Nobody suspected the steel itself. Nobody suspected the welding method as a whole. The Liberty ship program was moving too fast, and succeeding too visibly, for anyone to look closely at what seemed like isolated minor defects. But a pattern was forming, one that nobody had yet connected. The cracks were not evenly distributed across the fleet. Ships operating in warm water, the Pacific, the Mediterranean, the Gulf of Mexico, reported problems only rarely. Ships operating in cold water, the North Atlantic convoy routes, the frigid seas around Alaska and Greenland, reported them far more often, and the cracks that did appear tended to run longer and deeper. Temperature, it turned out, was not incidental. It was the trigger. Steel behaves differently depending on how cold it is, in ways that the engineers of 1942 had not yet learned to measure or predict. At normal temperatures, steel is ductile. It bends, stretches, and absorbs stress before it breaks, giving early warning through visible deformation. But below a certain threshold, steel can undergo a transformation, becoming brittle almost without warning, capable of shattering suddenly rather than bending gradually. In the icy convoy routes of the North Atlantic winter, Liberty ships were sailing directly into the temperature range where their welded steel hulls were most vulnerable, and no one building or operating them yet knew it. The reports piled up through the winter of 1942 into 1943. A crack here, a crack there, always repaired, always explained away, never fully investigated. The Liberty ship program kept building. The record-breaking launches kept making headlines, and in shipyards and dry docks across the country, hairline fractures kept spreading through hulls that looked, from the outside, exactly like success. Then, on a calm January night in Portland, one of those hulls stopped cracking quietly and broke all at once. By January 1943, the SS Schenectady was, by every measure the U.S. Maritime Commission used to judge success, a finished job well done. Built at the Kaiser shipyard in Swan Island, Oregon, she had been launched, fitted out, and put through her sea trials without incident. She had performed exactly as designed. On January 16th, she returned to the dock in Portland to complete final preparations before joining the war effort. Fully loaded, engines shut down, resting in calm harbor water. It was an unremarkable evening. No storm was recorded. No collision. No enemy action. Nothing to suggest that anything was wrong. The temperature that night hovered in the range shipyard workers would later come to understand as dangerous for welded steel. Cold enough to matter, though nobody watching the Schenectady that evening had any reason to think about temperature at all. Just before 11 o'clock, without warning, the silence broke. Witnesses on the dock described a sound like a rifle shot. Then another. Then a rolling crack that seemed to come from everywhere at once. The noise carried across the water loud enough that workers a considerable distance away stopped what they were doing and ran toward the pier. Some thought a boiler had exploded. Some thought the ship had been struck by something in the dark. What they found instead when they reached the water's edge was a fracture running across the main deck, visible even in the dim dockside light, opening wider by the second. The crack did not stop at the deck. It ran down both sides of the hull, through the shell plating, nearly encircling the entire ship. Within minutes, the Schenectady's hull had split almost completely in two, held together only by a narrow strip of bottom plating and the keel itself. The ship did not sink. The water was shallow enough, and the break came slowly enough, that she settled rather than went down. But she was finished, a vessel that had passed every test asked of her, that had never left the dock, that had done nothing but sit quietly in port, had broken herself apart from the inside out. No one died that night. That fact alone made the Schenectady different from several sister ships that would suffer complete structural failures at sea in the months that followed, some of them lost with their crews in open water, far from rescue. But the Schenectady's failure was, in its own way, more disturbing than any storm-driven sinking could have been. A ship lost in a hurricane could be explained by the hurricane. A ship torpedoed by a U-boat could be explained by the war. But a ship that broke apart on a calm night, tied to a dock, under no stress anyone could point to, that could not be explained away. It could only be investigated. The U.S. Maritime Commission and the Navy could no longer treat these incidents as isolated repair items buried in shipyard logs. The Schenectady had cracked in full public view. In daylight hours the following morning, in front of a shipyard full of witnesses and a growing pile of newspaper reports, something was wrong with the ships themselves. Not a handful of them, but potentially all 2,700, every one of them built from the same welded steel, launched at the same record-breaking pace, sailing into the same cold water that had likely triggered the Schenectady's collapse. For the first time since the Liberty ship program began, the question was no longer how fast America could build ships. It was whether the ships being built could be trusted not to break. The Schenectady's failure forced what months of scattered crack reports had not. A full, coordinated investigation into what was actually happening inside the hulls of America's welded cargo fleet. The task fell to a mix of naval architects, metallurgists, and researchers, working under the pressure of a war that could not simply pause production while they searched for answers. The Board of Inquiry convened by the Maritime Commission included some of the country's leading structural engineers, and their early findings ruled out the easy explanations first. This was not sabotage. It was not a shipyard cutting corners on materials. Every plate and every weld met the specifications the Navy had approved. That left a harder possibility, that the specifications themselves were incomplete, built on assumptions about steel that had never been tested under the exact conditions Liberty ships were now sailing into. One of the most important contributions to solving the puzzle came from Constance Tipper, a metallurgist at Cambridge University in England, who had been studying ship steel failures independently, as similar cracking problems appeared in British-built vessels. Tipper's research demonstrated something that ran against decades of shipbuilding assumption. The same steel that behaved safely, absorbing stress and deforming visibly before failure at normal temperatures, could turn brittle and fail suddenly, with almost no warning, once it dropped below a specific threshold. Her testing method, which came to be known as the Tipper test, allowed researchers to measure exactly where that threshold sat for a given batch of steel, a temperature below which the metal stopped bending and started shattering. This was the missing piece. The Liberty ships cracking most severely were overwhelmingly the ones sailing the cold convoy routes of the North Atlantic winter and the frigid waters off Alaska. The steel in their hulls, ordinary low-carbon steel of a type shipbuilders had used for decades without major incident, was dropping below its own brittle transition threshold in service, a threshold nobody had thought to measure before the war, because nobody had built ships this way, at this speed, sailing into these conditions, before. Riveted construction had never fully solved this underlying steel vulnerability either, but it had accidentally protected against its worst consequences. Each riveted seam, each overlapping joint, acted as a physical stopping point, a place where a crack running through brittle steel would run out of continuous material and simply halt. Welded construction had eliminated those stopping points in the name of speed and structural elegance, producing a hull that was, under normal conditions, genuinely stronger than a riveted one, and, under the wrong conditions, catastrophically more vulnerable, because once a crack started in continuous welded steel, there was nothing built into the design to stop it from running the entire length of the ship. Researchers at the Naval Research Laboratory took up the problem alongside academic investigators, running fracture tests, examining recovered hull sections from failed ships, and building a body of data that had simply not existed before the Liberty ship crisis forced it into being. The work was slow, technical, and largely invisible to the public, conducted in laboratories far from any headline. But it was establishing, for the first time in engineering history, a rigorous understanding of how and why steel structures fail suddenly and completely, a foundation that would prove far more consequential in the decades that followed than anyone investigating a cracked cargo ship in 1943 could have anticipated. For now, though, the war would not wait for a complete scientific theory. The Navy and the Maritime Commission needed a fix, and they needed it fast enough to keep 2,700 ships at sea without losing any more of them to the cold. Solving the science was one problem. Applying the fix in the middle of a global war, without slowing a production program the Allies depended on, was another problem entirely. The engineers could not redesign the Liberty ship from scratch. There was no time to halt 2,700 ships, pull them from service, and rebuild them with riveted seams. Instead, the fix had to work within the existing hulls, existing shipyards, and existing wartime schedule, a compromise built for speed, just as the original welding decision had been. The most immediate solution borrowed a principle straight from riveted construction, without abandoning welding itself. Crack arresters, thick strips of high-quality steel, riveted rather than welded into place at key points along the hull, were installed to physically interrupt any fracture attempting to run the length of the ship. The logic was simple and direct. If welded steel offered a crack, nothing to stop it. engineers would rivet artificial stopping points back into the design, recreating, on purpose, the protection that traditional riveted seams had once provided by accident. Existing ships already at sea were retrofitted with these straps wherever possible. New ships coming down the ways had them built in from the start. The second fix targeted geometry rather than material. Investigators had found that many cracks did not start randomly across a flat hull surface. They began at the sharp square corners of hatch openings and deck cutouts, points where stress naturally concentrated far more intensely than engineers of the era had accounted for in their calculations. A sharp 90-degree corner acted almost like a starting notch for a fracture, a place where steel was asked to bend stress around an angle it was poorly suited to handle. The fix was almost deceptively simple. Round the corners. Rounded hatch corners distributed stress more evenly across the surrounding steel, giving cracks far less opportunity to initiate in the first place. Shipyards began cutting rounded corners into every new hull, and where possible, retrofitting existing hatch openings, already at sea. A third layer of change addressed the steel itself and the welding process used to join it. Specifications were tightened for the grade of steel used at the most stress-sensitive points of the hull, favoring material with better low-temperature toughness where it mattered most. Welding procedures were revised and more closely inspected, particularly at points where multiple welds intersected, junctions that investigators had identified as common origin points for cracks, since overlapping weld seams could trap stress and create tiny defects invisible to the naked eye. None of these fixes were dramatic. None of them made headlines the way the Schenectady's fracture had, or the way Kaiser's 4-day launch record had a few months earlier. They were incremental, technical, and applied under enormous pressure, ship by ship, welder by welder, while the war continued and the demand for tonnage never let up. But together, they worked. Reports of severe cracking declined sharply through 1944 as the retrofits and revised construction standards spread across the fleet. The Liberty ship program, which had nearly been derailed by a structural flaw nobody had anticipated, kept building, now with a hard-won understanding of exactly what welded steel could and could not survive. The ships kept sailing. The question that remained was how much the crisis had actually cost, in ships, in cracks, and in lives. Once the full record was finally added up, by the time the war ended and the full record could be assembled, the scale of the Liberty ship fracture crisis came into focus, and it was larger than most people outside the shipbuilding industry ever realized at the time. Of the roughly 2,700 Liberty ships built during the war, investigators found that more than 1,000 had experienced significant hull cracking severe enough to be formally recorded and studied. That number alone made clear this had never been a handful of isolated incidents. It was a structural characteristic of the entire class, present in some degree across nearly half the fleet. Within that larger number sat a smaller, far more serious group. Close to 200 ships suffered fractures serious enough to be classified as major structural failures, cracks that ran through significant portions of the deck or hull plating, not just surface damage. And within that group sat the worst outcomes of all. Around 20 vessels suffered complete structural failures. Hulls that broke essentially in two, similar to what had happened to the Schenectady at dock in Portland. A number of these ships were lost at sea rather than safely at a pier, some taking their crews down with them in the cold waters of the North Atlantic and the Pacific, far from the kind of rescue that had been possible in a sheltered Oregon harbor. Set against the total production of the program, the numbers told a story of both success and hidden cost at once. 2,700 ships built, the overwhelming majority of them serving reliably for the duration of the war, and in many cases, for years afterward. But embedded in that achievement was a flaw that, left unaddressed, could have crippled the very supply lines the program existed to protect, and one that, before the fix was found and applied fleet-wide, had already claimed ships and lives that a better understanding of welded steel might have saved. The Liberty ship program remains, to this day, one of the largest and fastest shipbuilding efforts in industrial history. It is also, in the same breath, one of the clearest examples in the 20th century of what happens when a manufacturing innovation outruns the science needed to fully understand it. The ships that cracked. the ships that broke, and the ships that simply kept sailing without incident were all, in the end, built from the same steel, using the same methods, under the same wartime pressure. The difference between success and catastrophic failure came down to details, temperature, geometry, weld quality, that nobody had known to measure until ships started breaking apart to teach them. What came out of that lesson would outlast the war by decades. The engineers and metallurgists who investigated the Liberty ship failures were not trying to found a new scientific discipline. They were trying to keep cargo ships from breaking apart during a war the Allies could not afford to lose. But the work they did, largely out of public view, in laboratories and dry docks far from the headlines that had once celebrated Henry Kaiser's 4-day launch record, became the foundation of something that would matter long after the last Liberty ship was decommissioned. Among the researchers who carried the work forward was George R. Irwin at the Naval Research Laboratory, who spent years after the war studying exactly how and why cracks propagate through metal, building directly on the questions the Liberty ship fractures had first forced into the open. Irwin's research, and the field that grew around it, gave engineers a way to calculate something that had never been rigorously quantified before: the precise conditions under which a crack in a material would stop growing safely, and the conditions under which it would run uncontrolled to catastrophic failure. This body of work became known as fracture mechanics, and it did not stay confined to ships. The same principles used to explain why the Schenectady split open on a calm night in Portland now underpin the engineering standards used to design steel bridges, ensuring a small crack in a support beam does not silently spread until a span collapses. They govern the specifications for oil and gas pipelines, which must survive extreme temperature swings across thousands of miles without a hidden weld flaw turning into a rupture. They shape the design of aircraft fuselages and pressure vessels, where engineers must know exactly how much stress a material can absorb before a crack, once started, becomes unstoppable. Every modern engineer who calculates a critical crack length or specifies a steel's fracture toughness before approving a design is working within a framework that traces directly back to a wartime cargo ship breaking apart at a dock, because nobody yet understood what cold water could do to continuous welded steel. The Liberty ship program itself is remembered, correctly, as one of the great industrial achievements of the Second World War, a case study in what American manufacturing could accomplish under existential pressure, still cited today in discussions of wartime production and logistics. But the full record includes the other half of the story: a class of ships built faster than any in history, using a construction method sound enough to win a war and flawed enough to sink some of the very ships it built, until the failures themselves forced open a field of engineering knowledge that did not previously exist. The Schenectady never sailed again after that January night in 1943. But the questions her broken hull raised outlived the war, outlived the shipyards that built her, and now sit quietly inside the design codes of nearly every large steel structure built anywhere in the world. A lesson written into the material itself, learned the hard way, and never forgotten since.